Okay, so if we could use higher derivatives of the intensity, so also look at curvature, yes, we could solve it. Huh? But nonetheless, the optical flow algorithm that we will see is not designed to do that. And there's a good reason. So if you look at a local pattern, a very local pattern in a scene, usually this is not much more than the first derivative to go by, because usually the local the local pattern of intensity will be kind of a plane in 3D. You have a kind of planar change of intensity over x and y. So using higher order derivatives is not very useful, because basically it's a plane anyway, so these higher order derivatives would amount to 0. And even if you could measure them, there's a problem with high derivatives in images, namely that they are very, very noisy. So it's not even clear you want to go there, because if you try to get these high derivatives, you would have a big problem of noise sensitivity. We will look for a different solution though. Okay, and here it is. So what we do have so far is, and I will start a bit from the back, we have this equation, and that is the optical flow constraint equation. The equation that says that a point, a physical point, will keep its intensity throughout the motion. And if it perfectly does that, this expression, as we just saw, has to vanish. It has to be 0. But okay, we know it's approximate and so on. So at least this expression should be small. Okay? And then we want it to be small throughout the image, because remember, we want to extract a U and a V, a horizontal and a vertical motion component at every pixel in the scene. So this can be maybe negative at times, positive at times, but to make sure that negative and positive cannot cancel out, maybe a very large negative, very, very negative, and a very positive value cannot cancel out, we have a square. Okay? So all the values here, therefore, have to be small, because we integrate over the entire image. This is a double integral over the entire image. So at every pixel, we want this thing to be small in absolute value, basically. Okay, that's what we have so far. But as we saw, this is an underdetermined problem. We have just one equation, 2 unknowns per pixel, no hope for us there. So we throw into battle a second assumption, and that is this first assumption here, which is a smoothness assumption. It says that in typical scenes, neighboring points will have very similar motions. And that's indeed the case in most real scenes. If you have an image, you look at 2 neighboring pixels, probably they move kind of the same. There are a few exceptions. If you have a boundary between a foreground object and a background, for instance, if one point is on the foreground and the neighbor is on the background, they may move quite differently. But typically, neighboring points have similar motions. And that is what we express with this integral. Again, an integral across the entire image. Double integral across the entire image here. And we apply the same kind of philosophy with squares as before, but let me come back to that in a second. So what we say here is that if you have the horizontal motion of 2 neighboring pixels, Ux is in fact comparing the horizontal motion between 2 neighbors, that this should be small. They should be similar. The same for the horizontal motion between 2 vertical neighbors. Y. This is the derivative of U with respect to Y. So we are comparing the horizontal motion of a pixel and its vertical neighbor. And we say again, these should be similar. And the same for the vertical components. If you compare horizontal neighbors or vertical neighbors, they should be similar motions. And we have squares all over the place here. Here, 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 here. For the same reason as before. We don't want negative and positive values to cancel out. That's why. Okay, right, so we say, okay, we have the optical flow constraint equation, a pixel from one scene to the next, or from one frame to the next rather. We'll keep its intensity intact, but then neighboring pixels should also have similar motions. And as we will see, this additional smoothness constraint, which it is, helps us solving for the second component of the motion, the component orthogonal to the gradient. Because we are now dragging in information from the environment. We're using context. Remember that blob, where you saw the two components of motion, where you could see a bit further away, so that not only first derivatives, but also higher order derivatives could be estimated. Well, that gave away the real motion. Same kind of function from the smoothness constraint over here. So we have these two constraints. So note, we assume that both are small. That is what we will demand. This has to be small, not zero. We said this would be zero. It would really be zero everywhere. Of course, the integral had to be zero as well. We don't go that far. We are not that radical. We just assume this will be small. It is approximately true that this is zero. Okay. So that's the first thing. And the second thing is these squares. Notice the squares. Don't forget the squares. Okay, they are important. Because otherwise, large magnitude negative and positive values could cancel out. We don't want that. Right. Other remark. Integrals are over the images, both this and that integral are across the image over all the pixels. So we are integrated over the pixels. And finally, what we will now try to do, and that will require a bit more work on the theoretical front, is to minimize a combination of the two. So what we will do is we will try to minimize that in combination with that. We want both to be small. And the way we do that is to say, okay, we don't minimize that or that, no, both together as a sum, but a weighted sum. So we take the smoothness constraint, add it with a number of times lambda, this optical flow constraint, and that sum, that weighted sum, should be small. Now note that this lambda, of course, is kind of an engineering factor, and you have to develop a feeling for where to put it. It depends on your data. If the data are almost like noise slave, very pure data, you can put a lot of emphasis on EC, so lambda can go high. But if you have extremely noisy data, you may want to have lambda rather low and bring more smoothing through the smoothing constraint. It depends all on your problem, on the data. So the smoothness constraint not only gives you this component orthogonal to the gradient, it also helps you to deal with noise that you will have when you are trying to get at all these derivatives. Right? So data are not perfect, they are noisy. So you will make mistakes in estimating those. Alright. Now, we end up actually with the problem that's typical for the calculus of variations. So what we have now is that we want to minimize this integral here, this weighted sum of the two cost components that we have been introducing. Now what makes it slightly more complicated than a typical optimization problem is that this is not just a problem of let's say a function f function of x and then trying to find the x where f will go extremal. No, because what we have to find is not a scalar where we get an extremum, but a function for which we get an extremum. So that's why we say this is a problem of calculus of variations. So look for functions that externalize functionals. So the functional is the weighted sum behind the double integral here. And we have two functions that we have to return. A function u of x and y and v of x and y. What are the two components of motion throughout the image that make this thing minimal? So a horizontal component, u, at all pixels x and y, and a vertical component, v, at all pixels x and y. One, at the same time, adhering to the smoothness. Okay, so the problem is not finding some scalar, some x or something like that, that makes some function f maximum or minimum, but finding two functions u and v that make this this total expression minimum in this case. Okay, so we have to look for functions that externalize that functional. And notice f would be the functional, so that's the expression behind the integral. We will first go for a simplified problem, and I want to make that again. This is a first simplified problem. We have this function of only one, this functional of only one independent variable x. Remember, we have x and y. We forget about y for the moment. And we have a function here, lowercase f. Actually, we had u and v, but here we have only one function f, and then we have an f prime, which is the derivative of that function with respect to the independent variable. We also have that, right? We have ux and uy and vx and vy. So we have these two. But okay, first of all, we go for this simplified problem. We try to get the extremum value of that integral, looking for that function f that will make that integral indeed go into an extremum. We have some boundary conditions, so we assume that at the boundary constraints x and y, we have certain values, f1 for x1 and f2 for x2. Okay, now, what does the calculus of variations tell us about how to solve a problem like this? And this is probably something you saw in some course on analysis, but to be a bit self-contained, we want to repeat it here. So the calculus of variations will make the following reasoning. It is first assumed that we have the solution already. It would be nice if that would be true, of course, in all cases. So we assume we have the solution already. It's called f of x. That's the best function. That's the function that will drive this integral to an extremum value. And then we say, now, let's say we also have a test function, a deviation from f if you want. And we have not many conditions on eta, that test function. So that's the deviation from f that we will apply. There are not too many constraints on that. Of course, it has to have the necessary derivatives and so on and so forth. But here's an important constraint. We assume it to be 0 at the two boundary conditions. Okay? And the reason is that we will apply this sum. So we'll add a number of times epsilon is a scalar, this deviation, a function eta of x, to f. So we deviate from f, if you want, by epsilon eta. But if you have these two constraints here, the same boundary constraints as before still apply. So we're allowed to do that deviation in that sense. We'll still adhere to the boundary constraints. So we consider, in fact, instead of the original, this new expression here, where we have not f, but the deviation from f, by epsilon eta. And that's the derivative with respect to x. That's also why I said eta should be, well, we should be allowed to derive eta with respect to x. Right? So it has to have some continuity constraints. But other than that, we have no assumptions about eta. Only this and the fact that derivatives would exist. Okay, now if f is a real solution, that the optimal function, going away from that would be a very bad idea. So if you look at the deviation of this type, what would be the best epsilon? Well, obviously, epsilon should be 0. We want to stay where we are. F is a solution. Moving away from the solution by epsilon eta, bad idea. But whatever epsilon is and eta is, bad idea. Make epsilon 0, don't deviate. Okay, so this is the way we have, by the way, reconstructed this initial integral into this new integral. Right? Just to make that clear. So that's the transition we make here. So we replace f by f and the deviation epsilon times eta, where epsilon is scalar and eta is that deviation function. Right. Now, if f is a solution, then n deviation should result in something worse, right? And that would mean that the best epsilon you can possibly choose would be epsilon 0. No deviation. At 0 times epsilon. That's the best thing you can do if f is to be the real solution. But that now means also we have in fact reformulated our problem into a classical optimization problem. A classical problem as a function of a scalar. A scalar, in this case, epsilon. And that's the trickery here. Because we know what to do with that kind of a problem. So, with this trick we reformulate an optimization over a function, over functions in general, into classical optimization over a scalar, epsilon. And we know what to do with that. What we have to do with that is, of course, to say, okay, if you want to know the best epsilon, we have to derive I, the value of that integral, not the intensity here, by the way, this is not the value of the integral, sorry for the confusion. But anyway, what you want to do to optimize the value of I, the integral, is deriving it with respect to epsilon, and that should be 0. But we know, if f is to be the solution, then that optimum, this derivation being 0, should be met when epsilon is 0. So we know around epsilon 0 we should have this derivative vanishing. Okay, so let's now express what that means, because that will lead us to a condition on what f has to obey, what it has to go by. Here's the derivative of this expression here with respect to epsilon. You see epsilon appearing at 2 places. It's appearing here and it's appearing there. I'm then taking the derivative with respect to epsilon and putting epsilon to 0 yields these 2 components. Because it's here, so it's eta times f derived from f, and then it's here, so that's eta prime, derivative with respect to x, time f derived from f prime. And those 2 are there because, of course, epsilon is known to be 0. That's where we should find that extremum. We know that. If f is a solution, then that has to apply. Okay. So this is now kind of a condition on f, actually, for it to be a real optimum function. We'll have to play now with that constraint and see what it amounts to. So here we go. This is the same expression as before. And we will try to reformulate the second term. So that term here. And to that end, we will use integration by parts. And this is the condition, or the theorem, on integration by parts. So we have an integral between the two boundaries of the derivative of g times h. And this derivative after derivation amounts to doing basically nothing but taking the value of g times h at x2 and subtracting g times h at x1. So that's the value. Now, of course, this expression is the same as that expression, where we develop this derivative just into the two components that we have there. Okay, so this is an equation we'll now use to reformulate the second term in that equation on the top. So here we are again, and the way we'll use derivation of this integration by parts is by taking this derivative. That derivative amounts to this expression. That would be the expression in the middle on the previous slide. We know it should amount to that value. That was it g times h before on the previous slide? I think it was. Okay. Right, so, now if you notice, of this expression you only have that first part. That's what you have in that expression. This is what you don't have. Okay, we bring it to the other side. Okay, there you go. Now, we didn't have to ask much of eta, but one of the few things we had to ask is that it would vanish at the boundaries. So eta would be 0 at x2 and at x1. So this being the product evaluated at x2 minus that same product evaluated at x1 means at eta 0 at either end, this thing vanishes. And there it goes. So what that now means is that this integral here, we have it there, is the same as that integral. So we can replace this part, second part here, by this part here. And notice it has eta in there, just like the first term. So both parts will now have eta. We can bring it out. And there you go. Okay, so that's equivalent to the equation at the top. Now, it's kind of remarkable because this always has to be 0, independent of the choice of eta. And for eta, we could choose things that are quite peaked at different places. We could have a peak at one place, or another eta could have a peak at another place. And so. Now, mathematically, you can prove this can only be true. This thing can only be always vanishing if not this whole integral is 0. But also, this part of the integral has to vanish. So that part has to be 0 itself for this to always work, whatever eta, whatever acceptable eta you choose. So, this is in fact the Euler-Lagrange equation. Okay? We have the functional derived with respect to f, and a functional derived with respect to f prime, the derivative of f with respect to x, and here you have another derivative. Okay, Euler-Lagrange equation is called like that because it was actually detected or derived independently by Euler and by Lagrange. Both came out the same result, but not as a team in a European project, but rather as independent scientists. About 1744. Okay. Now, so far we have been telling a story about a function f, locate f, and a derivative with respect to x, and so on. But that's not quite what we have. We need two generalizations to really adhere to what we need. First of all, we don't have a single function f, we have two functions. We have u and we have v. Two functions we have to find. Horizontal motion components at all the pixels, so u as a function of x and y, and then the vertical component of motion, again, at all the pixels, so as a function of x and y. So, if you would look at the original Euler-Lagrange problem, this calculus a variation problem, but now not with one, but with multiple functions, f1, f2, and so on. What would you have to do? Well, you can follow exactly the same philosophy, but now to f1 you would add epsilon 1 eta 1, to f2 you would add epsilon 2 eta 2, and so on. And then you would demand that the derivatives with respect to epsilon 1 is 0, derivative with respect to epsilon 2 is 0, and so on. And that then immediately leads to a similar equation, but now for each function. So we have a function for u, f1, we have a function for v, f2, if you want. So we have a system of equations. We have two equations now, one for u and one for v. That went well. That's quite simple. The next thing is a little bit more involved, because we not only have, so that's the explanation here. We have two PDEs in it, right? Next problem is the second generalization, though. We don't only have an independent variable x, we have two independent variables here. We have x, but also y. Okay, what do we do with that? If you look at it, so if you start to consider the fact that you have a chain rule now where not only this factor with respect to x, but also with respect to y would appear, you also have two additional terms. So you have a function with the test function added a number of times, but then for the derivatives, you have also a component coming from x and a component coming from y. So now we have an additional part here. So if we want to derive with respect to epsilon as we did before and put the whole thing to 0, we have an additional part coming in from y. And we have to deal with that. So here we are. If we take derivative with respect to epsilon, as before, so we have a test function that we apply epsilon times, and then we derive with respect to epsilon, we demand that the derivative with respect to epsilon vanishes, we get this. And we have this additional third term. Now we can use something like integration by parts that we used before, but this time it's actually Gauss's integral theorem that is called for, because we have these two-dimensional integrals. So what does Gauss's integral theorem say? Here we have an integration over a domain, so a two-dimensional domain, an area. We have a function q derived with respect to x, and added that the function p derived with respect to y, and we have integration over the entire area. Well, the value of that integral amounts to the value of a contour integral along the boundary of that domain D, we have q di minus p dx. Right, so where does that come from? Now a small intermezzo to explain that. Probably you have seen that in an analysis course at some point. So we have this now. We will explain the first part, that this domain integral leads to that contour integral for that part. Okay, suppose this is our domain, the green thing here. This is a two-dimensional region over which we want to integrate. So we have this first area integral across that entire domain. And now we are claiming that that actually should be the same as taking a contour integral q dy. Now, in order to show that, let's subdivide this domain into these very small, very thin, narrow stripes. So you have all these narrow stripes here. You have to think of them as infinitesimally thin, actually. But as you will see, the value across the entire domain is just the value of the integral over each of these slices summed. Okay? So the value of the entire domain is the value over each of these slices when summed. Okay. So the question now is, what's the value of a slice? Well, so we see that we have these dx's here, coming from left to right to be like minus plus the neighboring value, plus minus this value plus that value, minus this value plus that value. If you look at this, the net effect of it would be is the difference between the value here on the right minus the value on the left. And of course, this is an area, it has a height dy, if you want. So that's dy. So that's what this slice will contribute. So if you look at all the slices, you have to just go over all the different slices, dq, dq, dq. Here, all the slices, every time taking the difference between the value right and left. If you go from the top here to the bottom, that's all positive, dy is positive, and then dy will turn negative when going back up. So that's where this difference is coming from. And of course, you don't only have that for the first term, it was the second term as well. The same applies there, same kind of reasoning. So that's how you arrive at this Gauss's integral theorem. Okay, here we are again. We have Gauss's integral theorem, and yeah, we have in fact only part of these derivatives with respect to x and y. So if you take eta times f derived with respect to fx, you have only part of that. This here, the second part you are missing. This is the value of that boundary integral on the right hand side. If you have so we know that has to apply given Gauss's integral theorem. Now, same philosophy as before. We know this eta. We don't have to ask much, but it should be 0 at the boundaries. So across this boundary here, eta is 0 everywhere. So this will vanish. Okay, that's 0. Now, if you look at this, that's actually the sum of these two. We know it to be 0, we just saw that. So we can just, as well, instead of using these components that we do have in our integral, use minus those. And then we get the same story as before. So this is an inequality, as we know. So second and third term can be replaced by this here. If we do that, we get this, eta again is brought out, and same reasoning as before. This now has to happen for all the etas we can think of, with the right kind of conditions, but there are still many, many functions that would apply. Now that can only be always leading to a 0 here if the thing between brackets itself is 0. So that is now the new Euler-Lagrange equation in case we have not one but two independent variables. And you see, it's the same as before, because that we had, but now we have this additional term. And the same as the term for x, but now for y. So that is the new Euler-Lagrange equation. Now we have to bring everything together. We had the first condition, we have not one function, but we have two, we have u and v. So that leads to a system equation. We have two equations, and we know these equations to also have to take care of two independent variables. So we have two equations, not of the original type, but of this type, with x and y. So we have two equations of this type, bring all results, the two generalizations, together. Okay, that's a new Euler-Lagrange equation with two independent variables. So now we have two of those equations, and here they are. We have the first equation for u, and then a similar equation for v. And we see they have this additional term for u, for y, in both cases as well. Now, what are these equations in the end? Well, what was the function? What was capital F? Well, capital F was this weighted sum of the smoothness constraint that we saw, and then this optical flow constraint equation. And that was this weight lambda that we saw before. So we can now evaluate the two equations. For instance, we have derivative of f with respect to u here. Where does u appear? Only here. Okay? So f derived with respect to u, partial derivatives, is 2 times lambda ix, and then the rest of the equation. So we have twice this times ISU and IYV plus IT lambda times IX. What is F derived with respect to UX? Well, that only appears here. So we have 2 times UX, but then we have to take an additional derivative with respect to X, so that's 2 times the second derivative of U with respect to X. And we have to do a similar analysis for all the terms in these two equations. And what that leads to are these two equations here. And we have here this symbol, nabla, which is the sum of second derivatives with respect to x plus y. This is kind of, well, it's a diffusion operator, basically. It's a Laplacian operator. So these are the two equations now that we have. And you see very well where different parts are coming from. So these two diffusion parts that just try to spread across the image information, that tries to get at kind of homogeneous U and V, that comes from the smoothness constraint, because the smooth constraint would of course be perfectly happy if there would be no change if you would just go to the average value everywhere for U and V. So that's what that is pushing for. Now the other term is pushing for this, and that's where the actual information from the image will be coming from. So where you have gradient, that will start to push to the value in these equations of the right-hand side. So the whole thing is actually driven by gradients. You need still gradients to make sense of this algorithm. Because otherwise the motor on the right-hand side will not function. Okay, so you have information coming in and then it's being spread around basically by that diffusion part. Now, in a typical image, your chances of really getting at an analytic solution for those equations is close to zip. Okay, it's non-existent basically. So we have to do this numerically. And the way to do that is then to go to evolution equations. So you get something like that, where I, in this case, is the iteration. So from one iteration to the next, you apply this as a change to U and V, until there's no more change. When this whole thing came to an end, no more changes happening from one diffusion to the next, so left-hand side goes to 0, that means that you also have reached your solution. All right. So there are coupled partial differential equations, by the way. But okay, we solved them numerically. Sometimes people use more than just 2 subsequent frames. Won't go into that here. But you see that indeed, and that's a point I've just made, the information will spread from points with a gradient. You need changes of intensity to drive the system. So the information will spread from edges, from corners, to the surrounding areas. But still, these edges and corners are needed, otherwise you won't get anywhere. This is an example. So in this case we have a sphere, it's standing on a still background, and it spins around a vertical axis, so you will see these balls spinning around. And then we start from an initial state where u and v are put to 0 everywhere. And then we apply these evolution equations as we just saw them. That very quickly brings up non-zero values to points where you have a good contrast and motion. So the edges typically. So those are the points where you typically first see a good motion appear. That is the motor of the system, and then that information will spread. So if you take 2 subsequent frames, so probably here in between 2 subsequent frames, there will never be really a convincing gradient. Neither will it be here. These points will depend on the surrounding areas to get their information. And that's what the diffusion is for. Diffusion does spread the information around. Okay? Otherwise, of course, you would not have a good solution. At other points where you have a gradient, remember, we only have the component along the gradient. The second component also has to be brought in by diffusion. So, okay, now let's look at this experiment here. This is a pure synthetic scene, but nonetheless, it's telling. We will take 2 subsequent frames from that scene, and we'll see that how from a zero solution everywhere, you very quickly evolve towards a non-zero solution, starting from the edges, steered, propelled by these edges. 0 at the beginning, and then very quickly, at the first iteration, you see information appearing near the edges and spreading out to the in-between regions until everything gets more or less filled. Now the resolution here is not great, in the text I think it's a little bit better. Okay, so remarks. If you would look at in detail at the solution of these equations of this algorithm, which is called the Horn and Schunck algorithm, near the edges, you will see there are still quite a few of errors remaining there. And that is because there is often a big difference between foreground object and background. That's why there is a discontinuity in motion, but it's not necessarily picked up by the algorithm because it assumes smoothness across edges of different objects. That is not true though. Also, this entire way of operating with the smoothness constraint, with this regularizer, this is an example of regularization, as we call it. It's a way of turning an ill-posed problem into a mathematically well-posed problem. And this is just an example, but it is applied at multiple occasions in computer vision for different kinds of problems. Here's an example where the car is moving forwards. This is the motion field. You see the center of expansion here, and then you have all these motions panning out from there. Here you see, in fact, different colors for different orientations. It's a way in which motion often is indicated, the Saturation indicates the magnitude, and the color, the orientation. So that's just forward motion. And then you have this expansion field, Star Wars kind of stuff. And then to end this lecture with, of course, the optical flow algorithm is just one among many, many ways of tracking objects throughout video sequences and so on. So there are many others as well. So some are really model-based, so they depend on a lot of knowledge about object. So like active contours, but also others that we will see in a second, an example form, also knowing it's a person, so there's a skeleton that you can track. And then there are feature tracking methods that follow just more generic things like corners or blobs and so on. There's also the condensation filter. I think it's still in the course text for those interested. And those are more general trackers. Now, tracking by detection is also a new area, and you will hear more about that probably when discussing deep learning. You detect something, and then repeated detection over time leads to a track, so you can follow in that way. Here's an example of one of these very model-based tracking schemes. It was done at EPFL here by our friends in the West. So we have an object, and we know what it is like, or we know what it's like. So this is kind of polyhedral model. You see some of the straight lines being highlighted, and it's fitted to the image, and then by keeping it fitted to the subsequent frames, you can know how its motion must be like in 3D. You see it being back projected and fitted back into the object, this three-dimensional wireframe model, in order to make sure that it's being tracked. And you see the power is still with us, which is always a good thing in COVID times. Similar problem, another box. So again, the wireframe model is available, it's being back projected and tracked from one frame to the next. And you see here some additional physical constraints that are being added for this ball, this virtual ball, to be rolling into the real box. And to end, this is an example where we try to do interfacing and look at what the human is doing, and that's being done by fitting a skeleton back onto the humans, knowing it's human. So again, it's very model-based, you know in advance what to expect, and that allows you to interpret the motion. All right, and that's it for this lecture. Next lecture will be about three-dimensional shape extraction. Thank you.